All right. Again, let's kind of keep going with this. All right, so we see these guys. I mean, again, the magnitudes of the currents are all the same. They're shifted by 120. So AB, we says it's 0 phase. This guy's 120 degrees. IBC is 120 degrees behind this one. This one is 240 degrees behind this one. Okay? All right. Now, let's say I wanted to relate the line currents to the phase currents. Well, how could I do that? Well, I just know by KCL, if I look at this picture, right, it better be the case that IA, right, what's that going to be equal to? This current enters this node, and then it looks like this current leaves it, okay, and this current here enters it. All right. So if I went in and I plugged these guys in here, right, IAB is I phi, right? This guy is I phi e to the minus j 120, sorry, 240 minus j 240. Well, that looks awful, doesn't it? I phi minus I phi e to the minus j 240 degrees. Okay? If I go through and I do that calculation, all right, it's not hard to do. What am I going to find out? Well, I find out that this becomes square root of 3 times I phi, okay, times e to the minus j 30 degrees. Okay, not hard to do this, right? I could put this all in rectangular coordinates and then go from rectangular into polar. Not hard to do. Basically, what do I find? If these are my phase currents, right, I can go through and do KCLs at this node, this node, this node, right, and I can figure out what the phase currents are. Effectively, what am I going to find? Well, I'm going to find that the line currents are square root of 3 times the phase currents, and then they end up being behind by 30 degrees. Okay? So IA, the first line current, the phase A line current, is root 3 I phi e to the minus j 30 degrees. Okay? Square root 3 bigger than this guy, behind by 30 degrees. IB, the B phase line current is going to be root 3 I phi, and he's going to be behind this current by 30 degrees. So that gives him a 150 degree phase shift. IC, capital C, again, root 3 bigger, and he's going to be behind this guy by 30 degrees. So that puts his total at negative 240 minus 30, or minus 270 degrees. Or I could call this, if I wanted to, square root of 3 I phi. Negative 270 is the same as 90. Okay? So let's sketch that picture then. All right, here's our imaginary axis. Here is our real axis. Okay? If this is IAB, and this is IBC, and this is CA, okay, then what this tells me is line current, IAA is there, okay, ICC is there, and 30 degrees behind over here, and a little bit bigger, is IBB. Okay? So in this case, they're 30 degrees lagging, they're 30 degrees behind, and root 3 bigger. So the line currents, okay, the line currents in this delta connection end up being back 30 degrees and root 3 bigger. Okay? All right, we'll use that in a problem now. Okay, so let's look at a specific problem. Let's say I was given this problem here in the back. Okay? So specifically, this is problem 11.19, all right, at the end of the book. So we're told the impedance, so problem 11.19, we're told the impedance in each line. Okay. All right. So here we are, problem 11.19. Okay. What we're told, we've got basically a setup with a delta connection of sources. Okay. Oops. They've actually done it this way, plus, minus. All right, plus, minus. All right, and then minus, plus. And then minus, plus. All right, so we're given line-to-line voltages. We're in a delta connection. We call those line voltages. All right, this is point A. This is point B. Okay, this is point C. Okay, all right, so this is here VAB, VBC, and VCA. All right, and we're told what those are. We'll get to those in a minute. All right, now this goes over here to our load. Our loads are delta connected. Okay. Okay. Our loads are delta connected as well. My loads are ugly. All right. This node here is labeled capital A. This one here is labeled capital B. Okay. This one here is labeled capital C. Okay. All right. So some definitions on our current. This guy here is IA big A. I little b big B. I little c big C. Okay. All right. So we have to find those currents. Let's think this through again. So, well, and again, maybe I should tell us the rest of what we're given here. These guys here, the impedances in the delta, we are told, are 100 minus J 75. 100 minus J 75. That is the impedance per phase. This is impedance per phase. Okay? All right? Now, what about VAB? We're told he is 13.2 kV with 0 degrees. Okay? We're told that VBC is 13.2 kV at an angle of 240 degrees back, and we are told that VCA is 13.2 with a negative 120 degrees. He's 120 degrees behind. Okay, so let's draw our arrangement here. Okay, here is VAB. Okay, here is VCA. VCA. Here is V. Let me be careful. These are little a, little b, little b. Let me VA, B, V, B, C. All right. All right. Those are for these voltages, and I'm trying to sketch them down here. VA, VA, B is here. VCA is here. VBC is here. Okay. All right. That's just how we've been told that they are set up in this particular case. All right. So, all right. What do? Well, the simplest thing for us is to convert this guy into an equivalent Y-Y connection. Okay. What does that mean? Well, that means that I need to convert this circuit, all right, into something that looks a little bit different.